this video I will teach you the conservation of energy and we will derive it. So again, we use this three-step principle in how to arrive at the local form of the conservation equation. Here it is now the energy equation. First of all, we define the controlled volume omega, where we calculate on the energy and the energy contributions and the energy transformation. So therefore we have to define the total energy. The total energy itself is the sum of the kinetic energy and the internal energy, and of course it's involved, or it's mass bounded, so we have an integral over the mass density multiplied by the kinetic energy and the internal energy contribution, the specific one. So this gives us the total energy. The total energy, based on the first law of thermodynamics, the rate of change of the total energy is due to the different forms of energy transformation. So the energy transformation itself is the right side of this equation, and the rate of change of the total energy is the left hand side of the equation. Of course, as we saw it before, the left hand side will be manipulated by the Reynolds transportation theorem, and the right hand side we have to discuss on right now. So the energy transformation. So the change of energy can be caused by several things. First of all, heat can be transformed in the volume unit by kind of a heat production term, which is, for instance, if we would combust something inside the volume, that we produce out, or we transform energy from chemical energy to heat, and this would be a unit volume term. Then we have some heat conduction of energy, which is kind of a heat flux over the boundaries. For instance, if we have some heat radiation or simply heat conduction. So this can be modeled by this heat flux term, and we have additionally energy introduced by the surface pressure forces, and additionally we have energy given into the control volume by surface shear forces, and finally we have some mechanical energy. And as I said before, then we additionally use the Reynolds transport theorem to manipulate the left hand side, and again these three ingredients will provide us the conservation of energy. For the left hand side we additionally use the conservation of mass to extract the density here, and this is more or less what the left hand side looks, as we had already the terms or the contributions listed before, and this is how conservation of energy looks in the local form. There is a possibility, and I would like to say you this in the context of conservation of energy, that we can rewrite the conservation of energy in terms of the entropy. Then we get an expression of the total change of the entropy on the left hand side. This total change of the entropy can now be used to define thermodynamic states, and this is very interesting because we are going to use it afterwards when we define the isentropic speed of sound, so we'll need it later. We can define the thermodynamic states. The first state we would like to define is the adiabatic, which means that there is no heat transfer on the surface, so the last term on the right hand side vanishes. Then this adiabatic case is not reversible. This means if we go from one state to another state and go back to the initial state, we are kind of will not reach the initial state itself, so it's not reversible. And if we would now say, okay, we would like to have a reversible state itself, then kind of shearing losses are not not allowed in the equations itself. The loss term is more or less the first term on the right hand side, and this means that in the isentropic case we are adiabatic and reversible, which means that we have simply on the right hand side a zero, and if furthermore the fluid would be homoentropic, this means that the fluid is homogeneous and the entropy is uniform, which simply says that the total change of the entropy is zero. And this is very interesting because this we can learn from the conservation of energy, and this is one of the key points using the conservation of energy for aeroacoustics,